Hello and welcome to the fourth in what is becoming a series on the coronavirus outbreak and how to do mathematical models with it. In this video, we're going to ask the question, how many deaths and will social distancing actually work? Will we be using the deaths as a measure for the efficacy of whatever strategy we have? This is a continuation of the previous video where we've developed a mathematical model. We're not going to have any sophisticated mathematics in this, but we will be running the program and looking at a lot of the results and implications. So the last time we wrote a program that produces the growth curve of the French epidemic. We'll be looking at that in more detail, the program. We tested our program to see how many cases we would predict, and we compared that to the observed number of cases. So we see that the red line there is the actual number of cases over the last 25 days, and the blue line is what we would predict with our model. Then we looked at a couple of different combinations of parameters. The contact rate, remember, is the number of individuals contacted per unit time by a typical infective, contacts that will be adequate to transmit the disease if the person contacted is susceptible. So here we've noticed that if the current contact rate we'll see is around 0.285, and if we could reduce that from 0.285 to 0.14, that is to say about half, we can see that the predicted number of cases would be from about 27 million down to just 10 million, but that will be a considerable savings in lives. Notice that if we reduce that to 0.13, the bump is even smaller, and if we get it down to 0.1, it's even smaller. Each of these curves that we've seen so far were produced by keeping the same lambda throughout the entire modeling process. And so the question arises, can you model a change in the policy, a change in the behavior, where we would have lambda equals 0.285 going along for a certain period of time and then change that abruptly by social distancing and see what happens to the curve after that. And yes, we did that a couple of days ago. It was day 23. Today's program will use day 25. So we can see that the number of cases we barely see, if you look down here around day 23, we barely see a change in the graph. We'll see in the application of our program today, we'll see exactly what that happens up close. But there we have reduced the curve and pushed it into the future. So this will be the switching, we'll call it switching from no social distancing to social distancing in order to see what kinds of benefits we can have from changing our behavior. So an important parameter that we'll look at here and we need to think about all the time in looking at epidemics is R0. R0 for our particular model is lambda multiplied times the length of infectivity or infectiousness of an individual. So lambda is the number of contacts per unit time multiplied by the length of time. And so this is the number of cases that are transmitted on the average by an infected person or contacts adequate to transmit. So the theorem that we usually prove mathematically is that if R0 is bigger than 1, the disease is growing. If it's equal to 1, the disease is stable. If it's less than 1, then the disease dies out. So for the lambda that we've chosen, and we'll see why, in the previous programs I used 0.28. I added the 5 there just to make the curves match up a little better. The rho, remember rho is the recovery rate, so 1 over rho is the length of time in the infectious class. So there we have, we've chosen 0.07. So the R naught that we're talking about right now that we have in our model is 3.99. We have to get that way down to 1. Can we do that by social distancing? So let's go down now to the program, and I'll give you a little tour of the program that we've looked at so far. This is just to change my working directory. Remember we had if we type in print defs with parentheses that will print out the definition of the susceptible, infective, and remove fractions, the total number of individuals, and the rates, the lambda rate and the rho rate that we've been talking about, the death rate due to the disease. So you can review that anytime you want to. We will not be running this because this is already in R, and so we won't forget that. Print DE actually gives us the system of equations that we're using to describe the transition. You can review that in one of the previous videos. And here I have a review. If we type in default inits, with parentheses, we get the default initial values that have been programmed into R. So now this is the actual part of the program that will be running. Step size is a technical term. The delta D is the death rate due to the disease. We have a lambda of 0.285, as we said. This actually analyzes that and gives me the solution. And then notice up here before going down, I've gone from day 1 to day 25. So, and down here in the second part, we go from day 25 to day 100. Later on, we'll pump that up to 200 and see what happens. But this is just to see the up close effect. We'll leave it at 100. So I've set this up now to plot the actual number of cases. And the first thing I'm going to do is run this with lambda not changing at all. So I change from lambda to lambda where I don't really change anything. So let's go back and run this program as it is. We go back here. This is in just a text file, so I have to copy this and paste it into R to see what the results are. So here I copy down to the study of deaths. We're not talking about deaths yet. We will in a few minutes. So I'm going to copy that and go down to R, paste it into R. And there I see that I have predicted about 27 million cases, and the outbreak around the worst of the outbreak, close to day 80 and 70 something. So the worst is yet to come. As we see from the real data, we're on this exponentially increasing part of the curve. I actually prepared an animation for you to let you see how this changes. Notice up here in the top, lambda is going down from 0.285 down to 0.096. And so you can see that the curve that we see that predicts the number of individuals who are ill, that it gets pushed into the future and drops down considerably. So that's a little animation there. I'll put in the link for you. As usual, I will give you all of these programs and data sets and everything that you need to run these yourself if you have if you're courageous and like R. So let's go back and look at another program here. We wanted to take deaths into account. You'll notice that this particular program is the same as the one we did before. I've got the same elements in the program, but at this point down here, what I'm going to go do is get the observed deaths starting at the 23rd of February. So I go back and get those actual observed deaths, and I want to come down and plot my predicted deaths against my observed deaths to see whether my model is good in terms of predicting what the deaths are going to be. So I copy that and paste it into R. And there we see that, again, the red line are the observed deaths, and the blue line are predicted, what it is that we actually predict the deaths to be. And so I think I have a fairly good fit there. So I'm going to go with those parameters. These are the parameters that we had in the other part of the model. Now that I know the full strategy, I want to go and see what happens if I go 25 days with beta equals 0.285. And now between days 25 and 200, I drop my lambda back down to 14. And now I want to see what it is, what the effect is of that on the number of deaths. So I'm going to go down and print out the number of deaths that are predicted by the model. So if I copy everything and put that in R, that shows me that, in fact, I've reduced simply by changing my strategy, instead of going up to 27 million, now I've only gone up to about 8 million, something like that, whatever this number is up here. I can find that out if I want to, because the infectives are Y1, and I can ask what the max of those infectives are. So that's going to be actually 8.6 million. So I have reduced it from 27 million, and I can see that my deaths, that's Y2, are my cumulative deaths. So if I look at that, I can see I've got 3 million deaths. But what is just that strategy of cutting lambda in half, going from 0.285 down to 0.14, I've actually gone down to 3 million deaths. And if we go back and look and see in the original death estimation, if I go back and look and see what happens if I don't change, if I take 285 and stay at 285, so I'm going to go in here for the rest of the time and change that to 285, and then go down and see what kind of deaths I have. I copy that, put it in R, and I can see if I look at the max of Y2, the max of the deaths, then that tells me that I've actually got 4.6 million, whereas before I had 3 million. So I've gone from 4.6 million here down to 3 million. So 1.6 million deaths that I will save if I can simply cut my lambda in half by social distancing. So let's go back and look. I want to take this and just look from 0 to 100. I'm going to go up to 100. I want to try some values here of lambda that are close to or just under point. They give me values just above and just below, or just close to R naught equal 1. So 0.09 I want to look at. If I use my social distancing in order to cut that down from 0.285 to 0.09, so this is roughly a third of the value that's observed in the data. Now, you see that I'm still not below R naught equals 1, so I can't kill this disease, but it's growing up extremely quickly until now I change, and by social distancing, it starts growing much slower. Now, so this is actually good, the effect of R naught getting closer to 1. Notice here also that my deaths are going to visibly start growing slower. So let's go back now and just put one more value in here before we go on. I want to look at 0.07. Now, 0.07 divided by 0.0714, that's going to give me an R naught less than 1, so I should expect my disease to die out now. So let's copy the program and plug it back into R. And there we see that if I am on this exponential growth curve and by social distancing I manage to cut my R naught down to below 1, then immediately the curve starts dropping down. And if I happen to do that, and I look at my maximum, which is the very last number observed in my Y2s, my deaths, that I've reduced the deaths down to 3,000. So social distancing will bring down R naught. R naught will, once it drops below 1, the disease will die out, will also save millions of lives. So please stay at home. And in the next video, I'm thinking about looking at the effect of asymptomatic cases. So what if we have people who are circulating around who are actually infective but don't know it and don't have any symptoms yet. So that's material for the next video. So I hope you enjoyed this. As usual, you can click on the link below and download all of the programs and data that I used for this video. See you soon. Bye.